can record from your side. All right, I just use this share the screen to look at. I have read your draft. My general impression is that it looks like the paper now or report now. But if you look at detail, I don't know what reason you say you don't. You can't. The text is fixed. You can't do anything about text. Are you prepared? Are you prepared to keep the text as it is now?
That's what I was thinking. Yeah.
Okay, because it's up to you. Because because I noticed an improvement from the previous one, but there are many potential to many aspects to be improved.
Okay.
Well, of course, we're talking about after that some of the apparent errors. Right? You hope to know, right?
Yeah.
So the in general, so I don't know the format you require. Normally here you would just put your name.
I cover my name on it.
Yeah, you put your name here, and that's
I'm not allowed to.
Oh, I see.
Because it's being sent off to some random person around the world.
Random. So, okay. All right. Understand. Oh, in that case, that is format. Accept that. And let's go to directly go to the body. Research questions. I think that's okay. Let's just go to first comment about the choice, the form of the equation. I think this is I would suggest you write another form is without using capital D. It's what is called a total, right? I would prefer to use this one. Do you remember? So that is just this partial derivative and T, and that what that is. This is more elegant. Okay, and also it's relevant to the notation you are going to introduce in your first place. Do you agree?
Okay.
Because if you write in this form, people will have to ponder and say, what is capital D? Okay, nobody writes this D except when in this context, and people have been studying that. Various talks question for a while, so that gives people some of the appreciation that what is relevant of this notation in Laplacian. I think it's yes, is doubt here. Yes, it's doubt here.
Yeah.
Another thing, this is the first comment. The second comment is that when you write the vectors, right? Do you mean this is vector or?
Yeah, that's vector.
It's quite rare because in the mathematics people write vector in this way, put it this way, which is odd. I mean, I wouldn't use that. So my suggestion is that don't use that and don't use that, because you can use a bold, you can use a bold, you can use bold font. Why don't you use this V or this V? Okay, let's use V. Okay, now and also I noticed this is not just one occasion. On many occasions when you give an equation, you didn't explain. That is bad. That's bad habit. Because the reader expect the equation is not just for good looking. They expect to know something. For example, you say, hey, let's go to Hong Kong. Okay, say, wow, you see what is a famous building, what is a famous shop. So people at least have the glimpse of what I'm trying to say. Okay, so I strongly suggest you write here, because you usually use UVW, right? UVW, right, as 3 components. And that's just velocity. The velocity that is relative to the frame of the standing still, right? So that is a way to I think that would be the way I introduce the formula.
But I think I mentioned it. In this table, I say I have the UVW.
Okay, let's go to your table. Oh, that is afterward. Yeah. Afterward, yeah. Where's your I noticed you have table somewhere. That is
yeah, it should be section 5.
Section 5. Oh, that's, you see, that is you see, people, if I'm a referee, okay, if I got this copy and expect to give some comment or marks. And I would just want to be more, I want to be more economic way to do it. Do you understand?
Yeah.
If you say, oh yes, if you know this, if you want to know this notation, then go to page 17. If you want to go to the page 5, it's time consuming, right? Why don't you just? I think somewhere you can. My habit or my recommendation is that whenever you give the equation, you tell people the note, the symbols, what the symbols are. But in this case, of course, you don't have to mention all because I notice you are going to just spend some section to discuss this DAO or the Laplacian notation, right? So that's my remark on this notation. We will come out some idea to improve that. Yes, so you're starting with the DAO I call it lambda, yeah. Well, normally you just call it DAO. You call it lambda, right? Lambda, yeah, which is yeah. Here, if you mean this is you have to also specify here because EI is presumably that is a direction of vectors, unit vector, right? So that should be the vectors. It should be written into vector form. That's the third comment here. So that is EI in equation 2, right? Shall we write E with bold? Yeah. Bold front EI. That is directional option. Okay. So that's just some details. Here you introduce how to denote the gradients. Okay, that is. Now here also, because I know you are trying to save, trying to, control the number of words. I think it's still you still have, if you can give people some one sentence or just indicating that, for example, so where f is a scalar function, just ordinary function, right? F is scalar, right? Presumably, yes.
Okay.
F is scalar, so you have to say you.
But I said in the last line, I say it transforms a scalar valued function into a vector field.
A scalar value function, yeah, is in that case. Why don't you say when you say blah 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 blah? I just call the scalar function. Can you see? So yeah. that's why I think that you scalar function. I would just call it scalar function, or in line with a vector function. You just put a set function and comma and put f, and then continue. All right. So that gives some people introduction of what f is. Right. You don't have this. You don't. This is some make it to show that it's easier to read.
Okay.
Divergency, yes, that's yeah, it's fine, and that will give you a scalar, right? Laplacian. Now this is so do you have to explain? And sometimes we just this is presumably this is a general form of the Laplacian. Do you agree?
Yeah.
So I think in general, so in many cases, because we just expect to write that as the delta. Do you see the delta, right? Delta squared.
Yeah. Oh no, it's just delta. It's just delta.
Delta squared. Oh, it's upside down. Sorry, it's upside down. It's delta. Oh, yes, that's right. That's right. That's just other way around. Yes. So that's right. That's just other way around, like delta, right? Yeah. So I think it well depend because there are many relations like this in the vector field analysis. This presumably that this second term show up if the cross product, what you call it, vortex equal to 0, right?
Yeah.
So if you are not dealing with a vortex. Oh, by the way, throughout your paper, I didn't notice you mentioned turbulence, the word turbulence. Did you?
I think that's because I'm not able to model turbulence in my hand solutions. So it only comes up in the CFD at the end. So I can't really talk about it very much. That's
All right.
It's not a very big thing in mine.
Yes, I mentioned, I will talk about that. That's okay. Let's go next. This is a formulation program. The title probably needed to be adjusted. If you are talking about this diagram, okay. Oh, so you are talking, this is just the beginning. You are talking about the whole things, this 5, that is a inlet condition. Inlet condition?
Yeah.
Just inlet?
Yeah.
Or probably they just in the formal description is there's 2 types of the condition. One is initial, another is boundary. So any of these involve.
But boundary conditions aren't really mentioned in this. I kind of mentioned those when I'm actually doing my problems. In the second analytical solution, I mentioned them.
Well, both in your simulation, you have to use the boundary condition. Otherwise, how can you tell the computer to start with, or when the iteration reach to the boundary, involve the boundary element. Well, this just I just read you this route, this one, justification of assumption. Okay, that's right. Yes, I think that is a little bit weak. In terms of the title, because you are talking about I'm going to formulate is a problem, right? And what you just provide is one of these. I know this diagram is important because that will give you draw people's attention. I'm not going to. That is exactly the model I'm going to use.
Yeah.
To study the flow, and then again to just a comment. So in this diagram, you have probably mentioned that. Of course, the picture speaks itself, and perhaps you will also just notice in your caption, in your figure 2, your figure 2 caption.
Yeah.
I just number 5, so the caption figure 2. So we'll say, for example, where D is the diameter, right?
Yeah.
Such detail is important because otherwise people have to, you don't expect people to know everything. Even he's a person in the field, right? Because you see, people know, as you can see, if you look at the different publication and textbooks, people use different notations. So that's why I think we have to. You see, if you use this D for parent, then if you return to my first comment, and the D come from appear here, you see, the D appear here, right?
Yeah.
So people get confused, you see. So does that D mean that D, right? Of course they wouldn't. They were if they're expert, but still it's a little bit confusing, right?
Yeah.
That's my comment. Let's go. We have to go through all these papers. So justification of assumption.
Because I say that D is the diameter there. If you look in the table. Second table.
In second table, yeah. Second table, yes, that's right. You have yes, you have the diameter here. You have the flow rate. Flow rate, yes. Well, I think if I were you, what I'm going to do, I just making a table, okay, just a single table. I just draw part of that. I put all this notation. This is notation or symbols. Notation. Sorry. Notation. And the symbols used in this paper, right? So then we'll use, for example, P for pressure, and just mention D for diameters. So do you understand? I just think as a reader, I just need this. Where is my?
That's what isn't that what I did there in the table?
Mm-hmm.
That's what I did.
That's your, yeah, that's right. yeah. Yeah, that's something we need to be explained. Okay, that's fine. So that is again, that's why in that case, this section title doesn't reflect what you actually talking about here.
Okay.
Well, we keep that as it is, and we'll go back if we have time. When you formulate, why don't you say the I wouldn't use formulating. We just because we this is just modeling. Can we say modeling?
Okay.
It's just for because this is all related to the model you used, right? You just use a proper diameter and proper, the flow rate. I think it's modeling, right? Modeling of the problem. Okay, modeling the problem. So that's my comment here. Okay. 6. That's modeling. Probably modeling is relevant. It's more relevant. Modeling the problem. Okay. Next comment. Because these two tables belong to are not in the same category, right?
Yeah.
So I still put the comment here. I wouldn't just mention the boundary condition, initial and boundary condition.
Okay.
That is the keyword here if you want to talk about mathematical solution of this problem or simulation. Justification, yes. Well, in that case, just the assumption of the blood property that could be part of your modeling. Do you agree?
Yeah.
So that would make sense if you say modeling, right? So you just, if for example, you say blood is, treat blood as Newtonian blood. This is not a formulation. It's just an assumption of your modeling.
Yeah.
Okay, that's a little bit small things here. That number 8. So this is 2 words. This is Latin. It's Abbey, initial. Okay, initio actually. So this is not English. Be careful. So there's space. There's space between. You don't write it as a one word. Okay, that is something which means from the beginning or from scratch.
Yeah.
Yep. Okay, this is where I get a little bit lost. Why do you have to introduce J? Is that absolutely important, or you found it more convenient to introduce the Navier-Stokes equation?
That's not. I'm deriving Navier-Stokes equations. So that formula there, equation 10, is Newton's second law.
I wouldn't write Newton's law in that way. Newton's second law, as we all know, Newton's second law is just F equal to dP dt. Do you agree?
But
P is pressure. Yeah.
It's more difficult to derive the equation if you do it that way. It's more convenient if you have like the different force terms. It's easier to do it that way.
You know what? The stress and this arising from is viscosity. Okay, in fluid, that is the problem. Apart from this, gravity is irrelevant. The gravity just creates a constant potential, right? Now, the force involved in this case is a viscosity related force. Do you agree? Yeah. So basically, what you do, so in my opinion, so that so if you put if you follow your rule, so what I do is I just say this is a number of force. Yes, I can use the sigma here. Number of force relevant, right? And some are pressurized force, others just due to the viscosity, right? Because they have internal or simply says internal friction, right?
Yeah.
So so in this case, we can direct it. So if we just use if we just consider the unit form, so we just divide both sides. But before that, can we just write n M could be for the particular cells. Yeah. So that is that with V dV. So I can immediately write that. So that dV dt. That is applied for any cells. So here we just rewrite that one. We still rewrite that one. Can you see? I remember in many textbooks on this content on these issues that they just simply divide by V. So they're discussing the volume. So you discuss the V on both sides. So then they just immediately you got this form. So that is what you call the total. Is a total derivative. In that we just use a small f, just a small f. Can you see?
Yeah.
I mean, of course you can keep the way you're doing, but basically if you write Newton's law is in my opinion, this is Newton's second law, right? Now if you added the additional J here, it's called the momentum flux here, and you have to explain. You need to spend more words to explain.
But didn't I explain it at the top in that paragraph?
Okay. Newton's second law to infinitesimal field element. That's right. According to Newton, the force acting on the body is equal to the time rate change momentum. However, unlike a body moving through space with a finite collision, fluid element collide with adjacent particle in incomputable rate. No, I don't agree. If I'm referee, I don't agree. Let's go to the original issues. Is this just a mathematical problem? You see, I don't know how did you get there, but I just have to remind you how do I change this. Oh, I run out of battery here. Okay, not just it's just come from here. I just okay, that's where. So just so what I'm doing. So we basically are dealing with the element here, okay, or it could be the three-dimensional element, right? Mm-hmm. So to apply Newton's law to, of course, there are hundreds or even millions of them, but in general we can just simply use vectors. Use R, can you see? Is what in math is called this origin is called the position vector. Do you agree?
Yeah.
So the R is the position of these cells, right? So that can be written as x, y, z, x, y, z. Yeah. Oh, by the way, also you completely abandoned using the polar coordinate. Of course, it's something different. I will talk about that later. Okay. So basically, by definition, so the dV, that is what we are looking for. So V, sorry, we got it. This is second derivative now. If you find the V, if you want to use the V velocity, it's just equal to dr dt. Do you agree?
Yeah.
Or you should just write the matrix form that would be x dot y dot x z dot. Okay. Okay. Mm-hmm. Then we come to that's the second derivative or acceleration. So that is acceleration we are interested in. So basically what we do, I think at some stage I have to show you. This is just like the how to say the so it's like so how to do that. So first you have to do that is a partial to the V itself, right?
Yeah.
Per self. And then you have treated all of this is a variable.
Yeah.
Okay. I think we have mentioned that before. So basically, you do that. Is in this case, it's hard to write the whole things. Before that, can we just rewrite this as use your notation? That's U, V, W, right? That's three components.
Yeah.
Okay. So basically, if you just go to component, I just show you. This is component. X component of the velocity, right? Then that will equal to partial U, partial derivative t, and then we have in this case we'll treat each U as function as the three variable, Because unlike, so that in this case you have to u delta x, right, and the delta x or delta x delta t, right, partial derivative here.
Yeah.
So because that's different, because unlike, so because it's moving, so of course the cause of this moving is due to the frequent condition, right? But when you describe the motion, we don't care the cause. We just follow this mathematics, because that's my, so that is how, if you write all of them, if you treat this as a function of 3, so you have added another term, that's y and y dt, right? Do you remember this one?
Yeah.
And the du, and that is just stop here. So basically, I just write it short. So you keep that one. That is the total. That is this is u. Treat u as a function of time, and then you put the rest together. You get the eventually you got. So I just go to the result. So eventually, what we have, we got this dv vector, right? Became, if you put the 3 components together, that will become, you see the dot, this notation show up. You see.
Okay.
So I don't think it is, not because you claim that it's is incomputable, right? It is not. You see, of course, this is just another way to derive the total first derivative. Okay. So that matter, because things has been go that far, because obviously you have to do this for a while. I think we have to keep something there, okay? But I have to make this remark that it is just when you describe the motion or velocity, you don't have to know. You don't have to know that the cause, right?
Yeah.
Because here, because you see, all of a sudden you didn't tell author, you didn't tell reader anything about the GA. Can you talk about the GA here?
What's GA?
J, the flux, the momentum flux. The
yeah,
J.
I said that I chose to incorporate a momentum flux term that accounts for this momentum transfer. Okay.
Yeah. So when you write a report, people expect you to talk about something with continuity, right? And for example, if you give it equation 10, and as a reader, I would just expect you to say, hey, what can you do about this J, right? How do we formulate J based on the common sense or based on the any diagram or modeling, right? I know it's difficult, but I just make some remark, right? Knowing that there are some let's just continue then. We just go back to these issues. Shear stress tensors visualized. Yes, this is a matter of communication. So you have to tell people, tell the readers that how do we treat this force, the sigma F here, right? And of course, if you don't use a molecular model, molecular dynamics model, then you have to phenomenologically treat it as a cubic, right? Very small cubic, and the cubic had a well-defined surface, and then that surface between the adjacent elements create different types of stress.
I say that.
Okay, you see that?
Yeah.
And considering force term, computing internal force, yeah. The force will be right axis. Okay, that's it. That's why that you have to say that. So let's go back. Okay, that is the formula you have obtained from that diagram, the equation 12, right? And we'll have to spend time with. I trust it's okay. And can you just, from here, I just noticed that. Can you see? When you reach the equation 13 and onward, right? You will see these 3 terms here. Can you see that?
Yeah.
What is this?
Oh, so that just comes from the equation 12 when you
no,
simplify equation 12.
So when you see this, I don't have number. I'll just put a remark here. So when you say delta x, delta y, and delta z, that's just dv, the volume, dv.
Yeah.
The volume. That's why in this case I would just divide the volume. We're just considering what's going on in the unit volume.
Okay.
That's why the mass became density.
Yeah.
And the pressure term became the pressure term because the force were equal to, say, the force were equal to the pressure times the area, so dx dy. Oh, by the way, I didn't notice you have any coordinate. In this case, did you explain what is the coordinate? What is the direction of z?
Oh, that's in the diagram, figure 3.
Let's see. So which direction does the flow move?
Flow can go in any of the directions. I'm not specifying the direction of flow.
Okay.
You don't need to.
Right. Well, eventually you have to, because when you're talking about the pressure drops, and obviously the flow rate must follow one direction. You agree?
Yeah.
So just go back to this one. So if you say in this case, if you divide by volume here, so if you divide by volume, so divide this product, dv here, if you have dv here, and then you will automatically get you will get this cancelled. You got dz here, right? It is here, but I'm not going to that detail. So basically, that is that happened. I noticed that there's where is my note here? Where is your note? Okay, just go downward. Where is my note? Doesn't matter. We will go. We will see that. Yes. So just a remark on this equation 29, right? Yeah. And also I similarly I suggest you write into the form I mentioned, right? Not capital D, just in this case, so equation 29. So 29. I just because that's from the 28 or from 28 equation 28, and it's easier to see that this is more. This is more direct. This is more relevant to equation 26 to 28, right? So how to write that? That is a dot here, Okay, that is so I do suggest you write this term instead of D. Okay.
Okay.
Stress. Okay. So capital P is pressure, right? Capital P is pressure. Yeah. Okay, that's your capital P. You got dx. All right. I think that is another thing is actually because if one of the highlights of this research work or essay is that you are able you demonstrate that I can build the equation, Navier-Stokes equation, from basic law in physics, right?
Yeah.
I think this is one of the highlights. When you will write the report, you would expect people to see this achievement, okay? Because many people wouldn't have a clue, especially even how can they about this equation. How can they actually apply this equation? But
Yeah.
your role, one of important role or achievement, accomplishment in this study is that you actually demonstrate. You say, I can explain to you how to build this equation. Okay.
Okay.
And so then this point, this highlight, should be mentioned in your conclusion.
Okay.
Okay, but we're talking about your conclusion after that. Analytical solution. In this case, I noticed that originally we are talking about using cylinder coordinate.
Yeah, but I have to do some of my own maths. And because people always do it in cylindrical coordinates, I'm doing it in Cartesian because it's different, and I can do it as my own.
Well, if you use Cartesian, then you're actually talking about the two-dimensional flow, right?
Yeah,
it's not three-dimensional. It's two-dimensional. Because I remember if you use a cylinder, then you can actually assume that there's a symmetry. You can use a symmetry here, so the theta is independent, right? So that property is independent of theta. So therefore, you can actually study the radius or ratio direction dependence, right? So that's why you get this parabola, right? The profile here. And by the way, this is not 2D. If you rotate it by 20, a circle, you get the 3D 3D profile. Can you see that?
Okay.
In your case, you just assume that x. So let's just consider your coordinate here. So this is where is x? So x is so this is y.
Yeah.
No. X is constant. So x. This is x. This is your x, right? This is your x. This direction of flow. So this is y. Do you agree?
Yeah.
Is this coordinate you use?
Yeah.
This origin here.
Yeah.
And okay, so the independent of y, right? So eventually the result of I notice that this is a parabola here. Okay, let's go to that. So you still use the r, okay? So that is the two extreme is r. So this is r, and the negative r. I try to reconstruct your coordinate here.
I need to have a diagram for it. I'll add that in.
Where? Here? No.
I will. I have to do it. I haven't done it yet.
Yeah. Oh, yeah. I suggest you use a diagram. Use a diagram, and then you just plug into the equation. Where again, I think in component form, you got this one. That's 2D.
Yeah, it's 2D.
Well, why don't you mention that this is a simplified scenario where that the 2D motion flow is considered, right?
Yeah.
Because that's otherwise people have to guess what you are doing. Okay, that's right. I noticed that here is something I have to make a remark here. That is if you just jump to the equation 50, right? I don't think this is appropriate. Can you see any trouble here? So basically from equation 49, you just argue that the second derivative is equal to constant. Do you agree? Or negative constant. Do you agree?
Yeah.
Where a equal to this delta p divided by L divided mu, right? Yeah. So this is original differentiation equation. And then I don't think this is right. So what I can do this one is I just first use we use the another notation? Can we just use see here? Oh, this is not right. If I just I can't do anything here. What I can do is we can rewrite. Say, can you just rewrite this question? Oh, by the way, because it's just one variable that we don't have to use this a curve, right? We just use you just d, okay? So what I can rewrite this question is rewrite this question as y du dy equal to negative a. A is defined by these ratios, right? Then we multiply dy on both sides. We got du dt, right? dy, sorry, dy. This is dy, okay? The second derivative is dy. So this is y. Then that became a dy. Can you see? Then we integrate it once, okay? We integrate on both sides once. And these two cancelled. That became dv. That will give you du dy equal to, and that will just add y apart from a constant, right?
Yeah.
Proper constant, say c, yes. And then we just, what we can do, so what we do, we just time dy again, so that du will equal to, that is a basic calculus, right? So just is a dy here.
Yeah.
So what you do, you just is a, that should be the y dy plus c dy. See? Then you integrate once again. So that is appropriate to write this part. See, you got these two parts, a y dy plus c dy. Can you see that?
Yeah.
Just how to move that downward. Oops. Oops. Move downward. Okay. So this is, so basically this is not right. So if you submit it to if you send to the referee, and certainly this is not right, because this got a two integrate, it's double integration, right? But you have one dy here, so this is not right. Okay. And also, you see, this is not right. This is basically, you say you have to be careful. This is just calculus. I wouldn't do that. I wouldn't do that. It's impossible.
Okay.
How can you solve this problem? You can't solve this problem. There must be something here. You must have something here, right?
Yeah.
You cancel. Then you got u, and you can got u here plus a constant. Okay, that's just calculus. So be careful here. You have to do some correction. And it's gonna move downward. That is a result. Velocity distribution velocity. Now, why don't you use this diagram? Why don't you use diagram to tell people which is x, which is y? Okay. Do you agree?
Yeah.
Why don't you take people this sorry, positive r, the negative r here, right? Because when you provide the coordinate, you have to specify the axis. Approximation pressure drops. Oh, if you go back, I think it depends on how much time we have. Yes, we have time. We have 15 minutes. We have. So here in this you now these have the notation of these two notation here. Can you draw your attention to these two, right?
Yeah.
Why do you put the I there? RE, so Reynolds.
Oh, so that's the because the Reynolds number would change whether it's at the inlet or at the center of the stenosis. So RAI is the Reynolds number at the inlet.
Did you treat as a constant throughout, or do you treat as a variable?
No, it's not a constant because the velocity changes. So you can't treat it as a constant.
So in your model at a different position, the number are different, right?
Yeah.
So the value you get is at this at what called inlet here, right?
Mm-hmm.
That's why you put I here.
Yeah.
Well, we will go back, but just some apparent. Why did you call the discharge coefficient? Is that simply called a flow? Remember, flow coefficient?
No, this is a different one, I think. I
Sorry?
used it in a different. That's it. It's different. It's different. I
What?
used it in the in one of my second analytical solution.
No. I'm just talking about the name of this notation. C sub D. C sub D. What do you call it?
Discharge coefficient.
Why is discharge?
Because that's just what the convention is.
Double check that. Okay, I would just call the flow coefficient. Okay, double check that. Discharge. Okay, I at least I have noticed that name, but you see, you have to make sure that when you use the name, and you have to assume that people will follow you, right? Can follow you, but
Yeah.
I can't follow. So I wouldn't just use call it flow, because it's a property of flow, right? Oh, by the way, are you actually serious using these Reynolds numbers in your discussing?
Well, I'm not sure. I think I might remove that part.
The reason you put this number here because what? Because you have in your simulation you use this number.
Yeah.
Or do you have to?
Yeah, I do.
Well, its Reynolds number is just a ratio, right? Isn't it? It's two force. You know, the inertial force over viscosity force, right?
There's a simpler formula for it. It's like rho v on A or something.
Yes, that's right. It's right. Yes, I just wrote to my note here. I think this is not as you don't have to mention that, do you?
It's one of the things I had to put it into my CFD.
So they asked you to do that. Okay, yeah. So that were equal to, I think that is a two force, right? That's inertia force and viscosity. Okay, I think I found the note now. Is no v velocity diameter and divided by this, right?
Yeah.
Yeah, it's just a ratio. It's a ratio. I'm surprising that because what is not that is a so when that are you able to trace this number if you think it's variable? Does this number increase?
Yeah, it does. It changes. I can't remember how, but it definitely changes.
Obviously, yes, there's a velocity here. That is explanation. You see. So then, in this narrow part, the velocity change. Okay.
Yeah.
So therefore, that would be. Yeah. Okay. This just you have to define. Let's go. Let's move on. Yeah, that's special case. Then you go to the simulation now. Not yet. Our pressure drop use Bernoulli equation. That's something I would like to ask. So this is number. This number uses two velocity, right? Obviously. Do you know the velocity change?
Sorry?
To calculate the pressure drop, what is the pressure? What is the ratio velocity you use? Is velocity 1, velocity 2?
Yeah.
So to obtain this number, did you use any particular parameters here?
1 second, sorry.
The equation 77. So the number in this
so you already know. So V1 is the inlet velocity. Which
this is V1. It's V1.
That's 1.2. The area one is I have a diameter at the inlet, so I can calculate that. CD is discharge coefficient, and everything else is pretty straightforward.
Okay. Well, does that mean this pressure drop is more reliable than the one you obtain from your simulation?
No, but it's an indicator. So if my simulation is completely off, then I'll know that I made a mistake. So I can go back and fix it.
I noticed that is a 2% relative uncertainty error is only 2%, something like that.
Yeah.
It's very close, I should say. It's very close because I was surprised to see. You see, the whole business, the whole issue here is that you in this way you obtain the DP, right? But that will be rely on the coefficient you choose, right? Coefficient V, and the Reno number. Do you have to use these two numbers?
You don't have to use Vernon's number here. No, I don't use it here.
You didn't use that?
No.
So what do you use? You use the initial velocity. So this is V1.
Yeah.
That's got this
and
A here, right? That thing that work to work at V2, right?
Yeah.
Okay. Okay, we don't have time to go to that detail. So basically, that is this number can't serve as a criteria or benchmark for your study, but it's just happened to be the case that this value is very close to. Let's go back to your result. We jump to this numerical solution. So we jump to that one here. Now, there's two numbers here, right? One is what you call the analytical. I doubt. Are you sure you call it analytical?
I think it is analytical because it's done by hand.
But how can you obtain this coefficient in the first place?
Oh, that's just it's just based on the surface. What the surface of the pipe is. So the discharge coefficient of an artery is 0.995.
If you use any parameters in your calculation, okay, apart from the binomial equation, then I wouldn't call it analytical.
Okay.
All right. We just use perhaps just from the binomial equation, right?
Mm-hmm. Okay.
Otherwise, you will put it down. Okay. So CFD is not. So CFD is not analytical. Well, the solution is there's no general solution analytical, right?
Yeah.
So I don't want to draw people's attention too much on this about this number, okay?
Yeah. Okay.
And also the subsequent relevant question is, does the second number, the d delta p CFD, is independent of the number of the iteration?
So the way it works is
how about this diagram? Can you explain this diagram to me?
Yeah, I explained it below. So all you got to really look at is the black line. So that's the first one.
This one. This one. Okay.
Yeah, that's called the continuity residual. And when that drops to below 1 times 10 to the negative 3, then that means your solution has converged. So that's when you take your answer. After that point, changes in the value are so small that it's negligible.
Well, at least from this diagram, I couldn't see that kind of, if there's any symptotic, right? Should you say symptotic?
It's not, because if you look at the y-axis, that tells you the change between two results. That's
this one, this diagram, is this diagram here?
No, one below.
This one.
Scaled residual monitor. Yeah.
Oh, but hang on. I can see that they will approach to the constant.
Exactly.
Okay?
Yeah.
Okay. So that means that the more the number, so eventually when the number reach to approach to infinity, then that will become the constant. You agree?
Yeah.
Well, in that case, I would just simply delete this second one. What's important to show this diagram?
Because that's just how you determine convergence. Whenever you CFD, you determine convergence is the point at which your continuity residual drops below 1 times 10 to the negative 3. And I explained that in one of my paragraphs.
Okay, so basically everything is dropping, right? There's residue, which means just the error, right? The error is just decrease. Yes, because I want to see. Can you explain this again? Can you explain this diagram here?
That one, so that's just
this number of the iteration, right?
Yeah.
And that will achieve the number that's very close to the number you obtained from binomial equation. That seems very interesting, but it's not so important, right? Is that important?
I think so. Because it means that my CFD is like very accurate.
All right. Okay, I think I just jump to the. Another highlight. Another highlight is you have also mentioned that you have this is a very good. This is evidence that you understand. To tell people you understand how to solve this complicated equation. By in this case, although the model is relatively simple, but you know how to use this important how to say finite difference approximation, right? So I would strongly suggest you mention these two in your conclusion. Okay, let's go to the conclusion. So in your conclusion, I didn't read much about. If you do want to talk about something here, I think you put this diagram into either into introduction.
Okay.
Because these two diagrams is irrelevant to what you are doing. Okay.
Sorry.
I don't think these are relevant. This diagram. Is CT? Is it CT scan?
Yeah. I think it is, because what we showed is we were able to calculate how pressure drop varies with percentage severity. And now on that graph, you can see 0.96, less than 0.5, 0.93. That's the percentage severity. So if I can get that data, then I can calculate whether a patient needs to have the operation done.
Okay, then if that is relevant, I will just discuss this issue before concluding remark. Okay.
Okay.
That's up to you. Finally, what is this? Where is this blue curve? What does this? Where is this? Where does this blue curve come from? This blue
that's
curve.
Just the polynomial regression. So those dots are at various percentage occlusion, various percentage narrowing. What is the pressure drop? And now I did a polynomial regression, and then I just found the point of intersect.
I see. You use a polynomial to model this curvature, right here?
Yeah.
Okay, yeah, I wouldn't do. I just in this case, because I just chop this down. I don't want to see this part, and it's quite confusing, right? Because you see that you just send the trend line. That's all. You just use scattering. You just scatter plot. You don't have to use. This isn't something I wouldn't do. Okay, because you see, you need to explain. Okay, and of course, the polynomial can fit any curve in principle. Do you agree?
Yeah.
So can you just draw these domains from here to here? That's all.
Okay.
Otherwise, people say, "Oh, what would happen? When that reach to the beyond 100?" No, it's meaningless. It's meaningless.
Okay.
All right. So that's just my remarks on your present draft, and so it's up to you. So, what
Okay.
is actually? Do we have chance to improve the text, the writing?
Sorry.
This is the final chance to improve this draft now.
Yeah.
Oh well, then we run out of time because I noticed you have done a lot of things original, and also the level is far beyond the high school level. But by reading your report essays, and I think there are many parts to be improved.
Okay.
It's up to you, and at least people, help people. Of course, on the other hand, if the referee or the examiners understand this written by high school students, I think that would be acceptable. But if you aim higher, and yeah, I can help you to improve that wording and the structure of this essay.
Okay.
It's up to you. Think about it. All right. So.
Okay. Thank
Okay.
you.
Okay. Yeah, welcome. So I hope you can get. You recorded that, so you can get his
Yeah.
note now. That's good.
Yeah. I
Okay.
wrote it down. That's fine.
Okay. Okay. Good luck, and I hope you will get a high mark.
Mm-hmm.
Okay.
Thank you.
Yeah, welcome. Okay. Can we stop here now?
Yeah, that's good.
Yeah.
Thank you then. Bye.
Goodbye. Note. Do we?